Good morning, students. Myself, Dr. S. Devikala, Associate Professor in the Department of Chemistry, SRM Institute of Science and Technology. In today's class, let us discuss about the topic stereochemistry. Stereochemistry is a sub-discipline of chemistry which involves the study of relative spatial arrangement of atoms that form the structure of molecules and their manipulation. That is how the atoms or molecules or ions or functional groups, how it is oriented in space or how it is directed in space. That is what the stereochemistry is topic about. First, we must know what is chirality or chiral. As we know, the valency of carbon is 4. So, if a carbon is attached to 4 different functional groups, if 4 different groups are attached to a carbon, means that carbon, you have to call it as chiral carbon. That has to be represented by means of asterisk mark, also star asterisk mark. So this carbon is said to be chiral carbon. So this center is called as chiral center. So a center that contains 4 different groups or atoms, that is called as chiral. A molecule or an object is said to be chiral if it is not superimposable on its mirror image. For example, human right palm and left palm. So if you keep your right palm over the left palm, these two are said to be non-superimposable. So they are chiral in nature. For example, here the lactic acid structure is given over here. Lactic acid is one having 4 different functional groups, namely hydrogen, CH3, OH and COOH. This dashed line, it represents the mirror. So to my left, what do you have? That is object. The other side, you can write the mirror image. If the object and mirror image, these two are non-superimposable, means then only it is chiral molecule. Then only it can show the property of optical activity. The other way, this is called the Fischer projection representation. The same lactic acid can be written like this also. So there are 3 different types of projection formulas: Fischer projection, Newman and Saha's. So all the 3 projections, they are useful in describing the molecule. That is the 3-dimensional representation on 2 dimension. That is, configuration of a chiral molecule is 3-dimensional structure always, and it is not very easy to depict it on a paper having only 2 dimensions. So to overcome this problem, the following 3-dimensional structures known as projections have been evolved. Let us see one by one. First one is Fischer projection. Again, the chiral center, chiral carbon is there. 4 different groups: H, OH, COOH and CH2OH. So what is the difference? This hydrogen, it is towards the viewer, whereas this OH is also towards the viewer, whereas COOH and CH2OH, these two are away from the viewer. So the characteristic features of Fischer projection will be rotation of Fischer projection by an angle of 180° about the axis, which is perpendicular to the plane of the paper, that gives the identical structure. However, similar rotation by an angle of 90°, it produces non-identical structure. The second one is Newman projection. Here we will be talking about front carbon and the rear carbon. Rear carbon is also called as back carbon. So in this Newman projection, the carbon atom away from the viewer, it is called rear, and it is represented by means of a circle. Whereas the carbon atom facing the viewer, it is called front, and it is represented by the center of the above circle, which is shown by a dot. So how to represent front carbon? Front carbon by means of a dot, whereas rear carbon by means of a circle. This is what Newman projection. So bonds joined to front carbon intersect at the central dot, whereas bond joins to rear carbon are shown as emanating from the circumference of the circle. So if you compare the front carbon bonded groups with the rear carbon bonded groups, means rear carbon bonded groups should be shown by means of shorter line when compared to the front carbon. Let us see. So this dot, as I told you, no, front carbon by means of dot. All the three hydrogen atoms or all the three groups attached to it by means of lines, somewhat longer line. Whereas the rear carbon by means of a circle, the lines shorter line when compared to the front carbon. So if you combine both front carbon and rear carbon, this will be the structure. This representation is called as Newman. Below what you are able to see, this is called as staggered conformation. All the groups they are 60 degree apart, whereas in eclipse closer proximity. Whenever closer proximity of similar group means the compound stability is less, whereas here two metal groups they are exactly at an angle of 180 degree, so they are highly stable. And the third one is Saha's projection. Here the bond between two carbon atom is shown by a longer diagonal line. So the lower end of the carbon, front carbon, the upper end of the line, rear carbon. The bonds linking other substituent to these carbon are shown by projecting above or below this line. So this center is front carbon, this is your rear carbon. The groups attached to it are shown by small lines. Again, like previous case, here also we have staggered and eclipsed. These two are called as conformations. So due to free rotation along the central bond, two conformations are possible. One is staggered, the other one is eclipsed. Staggered is more stable when compared to eclipsed always. So in this slide, you can see how to convert Fischer projection into Sagas. In order to convert Fischer to Sagas, certain rules we have to follow. Let us see. Fischer projection of a compound can be converted into Sagas projection first in the eclipsed form by holding the model in a horizontal plane in such a way that the groups on the vertical line point above and the last number chiral carbon faces the viewer. Then one of the two carbon is rotated by an angle of 180 degree to get staggered form, more stable or relaxed form. So here what you are able to see the Fischer projection. So the front carbon is going here, okay, whereas the rear carbon represented here. Then what we have to do? Rotation by 180 degree along C2, C3 bond. Where can you find C2 and C3 here? Your C2 and C3, these two are said to be rotated by what angle? 180 degree. As a result, you will get the conformation like this. This is how we have to convert Fischer projection to Saha's. Next one, Saha's to Fischer. Initially, what is given? Saha's projection is there. Again, what is the rule to be followed? Rotation by 180 degree. So your staggered sagas, first we have to convert to eclipse, from eclipse to Fischer. First the staggered sagas projection is converted in eclipse, then held in the vertical plane in such a manner that the two groups pointing upwards are away from the viewer. That is, both these groups are shown on the vertical line. Therefore, 2,3-dibromobutane staggered conformation, eclipse followed by the Fischer projection. Then how to convert Sagas to Newman, then Newman to Fischer. If you apply all the earlier rules, then you will end up with all the three. Whichever is required, that can be obtained. Then Fischer to Newman, then Newman to Sagas. Just for practice only. The important one is the conformational analysis. That is the conformation of N-butane. Butane formula CH3, CH3, CH2, CH2, CH3, or it can be written like this. The molecule can be viewed like this. Here conformation is nothing but simple carbon-carbon rotation. The molecule is allowed to rotate. So in case of butane, the rotation is taking place between C2 and C3. This is 1, 2, 3, 4. Here the rotation is taking place between C2 and C3. Due to this C2 C3 rotation, we are able to arrive at several structures. So these structures are called as rotational isomers or conformational isomers. So they are termed as rotamer or conformers also. So in this plot, you can see how we are arriving at a different conformation. That is starting from staggered, eclipse like that. First, let us see the structure, then we will see about this. One minute. So conformational analysis of N-butane, you can have eclipsed conformation as well as staggered conformation. In eclipsed conformation, if the groups are closer together, then it is eclipse. If they are away in terms of 60°, then it is staggered. Staggered conformation is always stable when compared to eclipsed. So here you have different types of eclipsed and staggered that is listed over here. Based on the stability or based on the energy difference. So here the antiform that is the most stable form of N-butane when compared to other other isomers. Next concept is isomerism. As you all know very well, isomers are nothing but compounds having same molecular formula but different structural formula. So isomers are further divided into structural and stereo. That is constitutional or stereo. Stereoisomers, you can also call it as spatial isomers also. So under this you have configurational and conformational. Under conformational you have rotamer, diastereomer, enantiomer and so on. Then you can have cis-trans. So first one, structural isomers. Structural, that is same molecular formula but different structural arrangement. So they are termed as structural. The other types of structural isomers are chain, position, functional, metamerism and tautomerism. The first case chain. Chain means skeletal isomerism. In order to remember easily, whenever you have the term N and iso, they are always chain isomer. N pentane, isopentane, N butane, isobutane. That is chain. They have same molecular formula. They differ only in the arrangement of carbon atom or skeleton. So they are termed as chain isomer. Next one, if the position of functional group differs, mean that is position. Always position isomer, they will be numbered like this: 1, 2, 1, 3, 1, 4. Same molecular formula, but the position of functional group, if it differs, then it is position isomers. The next one, functional isomerism, if the functional group itself, if it is different. If you count the number of carbon atoms here, 1, 2, C2, H6O. On the other side also you have C2, H6O only. But they have different functional group. Left hand side you have alcohol, right side you have ether. These two are different functional group. So functional isomers are nothing but same molecular formula but different functional group. So they are termed as functional isomers. The next one, metamerism. Here, as it is, if you count the number of carbon atoms, it will be the same. In diethyl ether also you have 4 carbon, whereas in methyl propyl also you have 4. But if you see the length, the distribution of carbon atoms with respect to the functional group, here the functional group is ether, O. On either side you have equal number of distribution. If you have unequal distribution of carbon atoms with respect to the functional group, then they are termed as metamers. The process is known as, the phenomenon is known as metamerism. So this type of isomerism is due to unequal distribution of carbon atoms on either side of functional group. So in case of diethyl ether, if you look at left hand side, you have 2 carbon atom, right side also 2. Whereas here in methyl propyl ether, right side you have 3, left side you have only 1. So that is called as metamerism. Then tautomerism means it will always exist as in equilibrium mixture only. One is keto form, means the other one is enol form. So isomerism, that is due to interconversion of one compound to another by relocation of hydrogen atom within the molecule. So the next one is stereoisomer. Under stereoisomer, we should see about the enantiomers. So non-superimposable object and mirror images are termed as enantiomers. In Greek, enantion means opposite. So the optical isomers can also rotate the plane of polarized light to an equal degree but in opposite direction. So the property of rotation of plane polarized light, that is what it is called as optical activity. Everybody knows very well. Enantiomers, as I told you now, non-superimposable object and mirror images. They can be represented like this, plus or minus RT or L form. Diastereomer, they are non-superimposable, but they are non-mirror images. That is the basic difference. Enantiomer means, I'll repeat, non-superimposable object and mirror images, whereas diastereomer means non-superimposable non-mirror images. So diastereomers are stereoisomers that are not mirror images of each other and non-superimposable. They can have different physical properties and reactivity. They have different melting point, boiling point, and different density. They have 2 or more stereo center. So examples given over here, you can have a look. So this also we have seen already. Chiral molecule, optically inactive, racemic. Chiral molecule, molecule with at least one chiral center. Optically inactive means not able to rotate the polarized light, plane polarized light. Racemic mixture, we know, equimolar proportion of D and L form. That is called as racemic mixture. Again, the concept of optical activity. So chiral molecules interact with plane polarized light. This is how the actual experiment has been performed in order to determine the optical rotation. The rotation is denoted by either plus or minus or in the form of D or L. D means dextro, L means levorotatory. That is, one is clockwise rotation, the other one is anti-clockwise rotation. So the instrument used is polarimeter. Here the optical rotation, it is denoted by the symbol alpha. So this optical rotation, it depends on several factors, namely concentration of the sample, length of the sample cell, wavelength of the incident light, solvent and the temperature. So this is the expression. Optical rotation is equal to alpha by L into C, where L is path length, C concentration of the solution. Alpha is nothing but optical rotation or observed rotation. For example, for this molecular formula C3H6O3, it represents 2 enantiometric lactic acid. One is D-lactic acid, other one is L, or one is plus lactic acid, the other one is minus. We have seen already, so I am skipping this slide. Next one, meso compound. Meso compound means it is optically inactive always. Why means that is due to why meso is optically inactive. The answer is very simple. That is due to internal compensation. Internal compensation is nothing but the rotation of one half of the molecule is said to be neutralized by the other half. Suppose this part, this, if you have the mirror over here, mean this chiral, you have 2 chiral center here. First asterisk mark, first center, the second one is second chiral center. So the rotation of this half of the molecule is said to be balanced by the other half, so that the overall rotation, overall optical rotation is 0, so that it is optically inactive. Then let us see about the different elements of symmetry: plane of symmetry, center of symmetry, proper axis of symmetry, and alternating axis of symmetry one by one. So plane of symmetry, that can divide the molecule into two equal half. In case of mesotartaric acid, this is the structure of mesotartaric acid. In mesotartaric acid, you have planar symmetry. Due to the availability of planar symmetry, mesotartaric acid is optically inactive. Then the second one is center of symmetry. So center of symmetry, or it is also called as center of inversion. It is defined as a point within the molecule such that if an atom is joined to it by a straight line which is extrapolated to an equal distance beyond it in the opposite direction, it meets an equivalent atom. In other words, it is a point at which all the straight lines joining identical points in the molecule cross each other. So for this molecule, this will be the center of symmetry. All the points meet at one common point, that is called as center of symmetry in simple words. Then the simple or proper axis of symmetry, it is nothing but an imaginary line passing through the molecule in such a way that when the molecule is rotated about it by an angle of 360 degree, an arrangement indistinguishable from the original is obtained. Such an axis is called n-fold axis of symmetry. For example, cis-1,3 dimethyl cyclobutane has a two-fold axis of symmetry, that is C2, rotation by 180 degree. It gives indistinguishable appearance. That is, we are not able to differentiate between the initial and final. And then the fourth one, alternating or improper axis of symmetry, reflection through mirror plane perpendicular to axis. So the example is 1,2,3,4 tetramethyl cyclobutane. It has S4. So the next concept is configuration. Configuration is nothing but arrangement of atoms or groups in space. How the functional groups are oriented in space. That is called as configuration. It has two types. One is absolute configuration. The other one is relative configuration. Absolute configuration is nothing but the actual arrangement of the atoms or groups in a molecule with respect to the stereo center. That is called absolute. Whereas relative means comparison. It is defined as the correlation between the different stereo centers within the molecule. So the position of atoms or groups in space in relation to or in relative to something else in the molecule. So in order to determine the configuration, we have to follow the Can-Ingold-Prolog rule. These rules are called as sequence rules. So what are the steps that has to be followed in CIP system means Can-Ingold-Prolog rule. Identification of stereo centers and double bonds. Assignment of priorities to the groups attached to each stereo center or double bonded atom. Then we have to assign whether it is R, S or EZ nomenclature. So what are all the rules to be followed? Let us see one by one. In the first rule, compare the atomic number of the atom directly attached to the stereo center. Stereo center, it may be carbon or it is carbon. The group having atom of higher atomic number means that receives higher priority. For example, if oxygen is bonded, nitrogen is bonded to carbon means oxygen is 8, nitrogen is 7, then oxygen will be the higher priority based on the atomic number. If there is a tie, both oxygen or both nitrogen means, then we must consider the atoms at distance 2 from the stereo center. Then we have to proceed to the next atom. Okay, the next element. As a list, it is made for each group of atoms bonded to the one directly attached to the stereo center. Each list is arranged in order of decreasing atomic number. Then the lists are compared atom by atom. At the earliest difference, the group containing the atom of higher atomic number receives higher priority. Higher the atomic number means that atom will get higher priority when compared to the other atoms. Again, if there is with the second atom also, if there is a tie, then we have to proceed with the third atom. If third also there is a tie, then we have to proceed with the fourth. Like that we have to proceed. So if you look at this Example you can understand easily. Four different groups are there. One is hydrogen, OH, NH2, CH3. So based on atomic number wise, oxygen, nitrogen, carbon. So 6, 7, 8. So higher priority with respect to oxygen only. So if you look at the second example, here you have CH, CH3, CH3, CH2, CH3, simply CH3. So the higher priority, you should, if you see, here also C, here also C, but here 3 hydrogen atom, here only 1. So accordingly, the priority with respect to this only. One more example, which is higher and which is lower. Left hand side, this group is lower, whereas right side you have higher priority. Accordingly, the configuration also it will differ. Left side you have S configuration, right side RS. Some more examples. So we have to assign the configuration for the following. This can be done as homework. I hope you have understood today's class. Let us meet in the next class. Thank you.